Okay, so I'm going to be showing the basic usage of my neural network API for my AQA computing A-level project. So to begin with, first of all, we must include the main class that the framework is defined in, so this network model.h class header file. And I'm going to test it on the MNIST dataset, so I need to include the MNIST data loader.h file as well. So to begin with, I'm going to load in the test and train sets for the MNIST dataset. So I'm going to define this variable called train as an MNIST data loader class, and I've just written the file locations up here of where it's stored on my computer locally. So the other two parameters, as you can see here, are one-hot and classes. Now, this is a training data set, so one-hot is what we want, and that's defaulting to true. And as it's the MNIST data set, there are 10 classes, so that's fine. So we just need to specify the file path, as I have done here. So then, because MNIST is specified under two different files, one for images and one for labels, we need to first of all load the main dataset using this function here and put in the name of that file, which must be within this folder specified here. And then the same for the labels of the dataset. So again, they're just in this file up here. So then we do almost the identical thing for the test dataset, so I'll just call this test instead. And instead of the train and trained images and train labels, we use these T10K files instead, so I'll copy these down here. Okay, and then, just so I don't forget later, I'm going to put at the end of the file to close these datasets once we finish with them. Okay, so I'll just label this as the load the datasets section. Okay, so then next we need to define a neural network model. So first thing to do is to create an instance of a network model, as was imported from this include statement up here. So this model will be the model that we're going to define and then later train. So first of all, we need to set the entry to the model. So this will define the shape of any input data put into the model. So for MNIST, they're 28 by 28 grayscale images. So 28 by 28 by 1 is the input shape. So for classifying unseen data and training against training data, we need to specify this shape. Whilst I could define it like this, it's a shape of 28 by 28 by 1, the loader class up here, the MNIST data loader class, the object actually has a function called load size, which I've defined, which will, by default for MNIST, return this shape automatically. So now we actually define the model. So I'm going to begin with defining a dense neural network model. So whilst this is an image stimulus, so a convolutional model would generally perform better, I'm just going to begin with a dense neural network model. So to begin with, as this is currently shaped data, as I said, this is loading 28 by 28 by 1 size images, we need to flatten using this flatten function on the model. So that will just, instead of being 28 by 28 as a square image, it will flatten it into a 784 long single string of numbers. So then I'm going to use a single hidden layer, which will be a dense layer, and it'll have 512 units. And this dense function will automatically create the weights and biases tensors to be trained. And as you can see, I could, if I wanted to, set a specific normal distribution that they could sample from with this variable initializers class, but the default will be fine for this model as it's quite simple. So then I'm going to specify a ReLU activation function. This just stops the model being linear, so it can learn more complicated data than just linear data. So then this will return a new tensor or vector, since it's one-dimensional, with 512 units. Since I said at the start the MNIST dataset has 10 output classes, what we now want to do is transform this down with an output layer into 10 nodes rather than 512, so it's actually usable. So again, I could just say this if I wanted, so because I know it's going to be brought down to 10. However, like with the load size, the MNIST data loader class has a classes method which just returns the number of output classes that the dataset is divided into. So the MNIST dataset holds numbers 0 through 9, so there are 10 classes, so this will return 10. Okay, as this is the output layer, I'm not going to specify any activation function for this. Instead, I'm going to specify an output function. So this is a special function added at the end of the model, and I'm specifying that it's going to be a softmax function, which will take each of the 10 classes and normalize them so that each value from each class is between 0 and 1, and 2, the sum of all the classes adds to 1. So this means that the output will act as probabilities of each class. So for example, if it predicted 1.0 for class 4 and 0 for all the other classes, that's 100% certainty that it thinks that the input data belongs to class 4. So the softmax function is good for this because it means it's a meaningful result from the network rather than just a set of random numbers. Okay, and despite setting this for this example, I'm not actually going to ever use the output function, but it's just good to specify one. So then, and we do actually need this, we need to set the cost function for the model. So the cost function will be how the model will measure the difference between two distributions. So it has the target distribution, which will be stored in these labels up here, and it has the observed distribution, which it will calculate. So it will then find a measure of how far away these distributions are from each other, and depending on how far they are, will give an indication of how well trained the model is, and minimizing that cost value will lead to a more optimal solution, because the difference between the distributions is lower, and hence the trained distribution is a closer match to the true distribution. So therefore it gives a better overall model, and obviously that's the desired intent of a neural network. So for this I'm going to use the softmax cross entropy cost function. It generally performs better than other cost functions on neural networks, so I'm just going to use this. The other option I could use if I wanted would be squared error, but softmax cross entropy basically always outperforms it, so I'm going to just use that. Okay, and the final extra function I need to define here is the optimizer function. So I'm going to use the Adam optimizer. So the Adam optimizer, again, whilst there are other alternatives, Adam generally performs better than them all, so I'm just going to use this one. And I have to specify the learning rate, so I'm going to just say 1 times 10 to the minus 3. This is, again, just a very standard learning rate that generally works for almost any problem, so that's the one I'm going to use. Now, that's the entire definition of the model, so that is 29 to 40, so 11 lines of code, including white spaces, to define a model. So that's all it takes to specify what the model is. And now the next thing I'm going to do is set up logger. So at the moment, if I tried to train this model, it would train. However, it would not display anything to the console or show any indication of how well trained it was, and it would be very difficult to tell if it was doing well and predict how long it might take and see how far through it was and so on. So the logger is quite important for overcoming this. So I'll create a logger, call it logger, and I'm going to specify that it will output a log on every full epoch, and that the verbosity of the logs is high. Now, there's 3 different options for verbosity. There's high, medium, and low. High verbosity will actually output a metric after every training step, so it will give the loss, the time taken for that training step, and an approximate accuracy measure. The accuracy isn't actually the true accuracy, but it gives an approximation of how accurate the model is performing based on the current cost. But as I said, again, it's not the true accuracy. Yeah, and then log per epoch will just give another log at the end of every full epoch that's completed, giving the average loss over the epoch and the time taken for the entire epoch and which epoch number it was. So now that I've created this logger, I'm going to call logger.plot, which will cause the logger to plot a real-time graph during the training process. So it will have cost on the y-axis and training step on the x-axis. So over time we'll be able to see if the y values or the cost is decreasing as time goes on in a curve that I'm kind of indicating with my mouse, that indicates that the model is learning successfully and the cost is being minimized, and therefore it's going to give a good distribution towards the end of training. So now that I've specified the logger and the model, I need to actually add the logger to the model. So I just call the add logger class function, and I add this logger to the end of this model. And then now that the model and the logger are all set up together, I'm going to initialize the model, which will set up variables and essentially set up like compile this model so it's actually usable. At the moment, if I try to train this, it would just throw an exception. So I need to initialize it to set it ready for use. And again, like I did with the data sets, I'm going to just uninitialize it before I forget. So that will go at the end. So then finally, well, not finally, the next step is to actually train the model. So this is very simple, because we loaded the dataset with this class up here, which handles basically everything. So it will handle batching, as I think I said. This specifies the batch size here. So we're using batch sizes of 512 examples per training step. So this will automatically load in 512 examples at a time, go through the file, loop back to the start after each epoch, etc. So all we need to do is call model.train and pass in the batch iterator, which this class extends from. Does it say here? No, it doesn't. But basically, all the data loaders within my API and other data loaders which extend from this batch iterator class, as long as they implement the abstract base class, they will be able to be used in this train function. So this train variable up here does extend from that class, so I can pass it in here. And now I need to specify the number of epochs which it will take, and an epoch is basically an entire iteration through the entire dataset. So the MNIST dataset has 60,000 training examples, so one epoch means go through all 60,000 examples one time, whereas 5 epochs means go through all 60,000 5 times sequentially. To save time, because I'm not trying to train a particularly amazing model at the moment, I'm just going to call it with one epoch for now. And then, as you can see, there's another function, another parameter here called from start. And basically, what this allows you to do is partially train a model. So you could train half a model in one time and then load in a partially trained model and continue training. So by default, this is going to expect to continue training. And as this model has just been created, I haven't loaded it from a file or anything, then this won't actually make any difference. It's going to start from the beginning anyway. As soon as it finds out that there's no checkpoint of how far through it got from training before. So that's all we need for training the model. So that line on itself will train, and also it will handle all the logging code. So it will produce a live feed of the graph, because we call plot, and printouts after each training step and epoch, as we specified here, for the different properties we asked for. So finally, we evaluate the model. So we've trained a model, but at this point we have no idea if it's a good model or not, so we evaluate it to check if it has trained effectively. So this will basically, what we can do is get a percentage accuracy. So so over this test set that we loaded up here, this has 10,000 examples, and what this will do, if I call model.evaluate on the test dataset, again, this uses the batch iterator class, so any class that extends from the batch iterator base abstract class and implements all the abstract methods will be able to be evaluated as well, and this will again handle batching and everything else. It will initialize the loader and everything, it just does it all for you. So what this will do is it will go through each example in the test data set, and it will run it through the network. The network will make a certain prediction, and then the prediction will be compared to the known answer, because this is a labeled data set, so each number in the data set has a corresponding label, so you know what number it represents, and if it's correct, it increments the correct counter, and if it is incorrect, it does nothing, and then at the end it divides the total correct by the total in the data set to give a percentage accuracy. Again, this accuracy is only an approximate because it's just on the specific data set, this test set, that it's performed with that accuracy, but it still gives a good metric. And as you can see here, I've multiplied it by 100 just to give it as a percentage, because this will just give a number between 0 and 1, and I want it as a percentage, so I've just multiplied by 100. So then finally I'm just going to print to the console the accuracy, just so we can see how well it did. So just using C++ printf function, just passing a float parameter in here and then percentage sign after it. That's all that's doing. So then that should be everything. So just to recap quickly, we loaded the data sets, the train and test ones for actual training and then evaluation. We defined the actual network model, so we had one hidden layer with 512 units, and then a final layer just to transform it to the right shape for the output. And we set up outputs, cost, and optimizer functions. We set up a logger, added the logger, initialized the model to allow it to be trained and evaluated and to have any operation run on it, and then trained it with this simple line here, got the accuracy with these two lines, and then uninitialized everything to free up memory. And yeah, just it's always best to destroy pointers, etc. once they're finished with. So if I run this, this should, presuming I haven't made any mistakes, compile and then train against the dataset. Okay, so here's the log. It's going quite quickly. Each step's taking around 40 or so milliseconds, and as you can see, the graph dropped significantly. It started around 2, I think, and then the ending up loss was kind of somewhere around 2.5, and it's still very spiky, but this is basically always the case. But as you can see, the general trend of the loss is definitely going down, and then it resulted in a model that got 92.2 accuracy, percentage accuracy. So that's not a great model, but clearly a lot better than randomly guessing, because you'd expect around 10% accuracy with randomly guessing because there's 10 classes. So clearly it's learned, and it's not produced a bad model at all, and took 14 seconds. So that is a dense neural network model on the MNIST dataset. So another thing we could do, which would likely improve the accuracy, and again, I'm not by any means intending to train a particularly good model, I'm still only going to use one epoch. We could, instead of using a flattened dense neural network model, we could instead use a convolutional neural network model. So a convolutional neural network, instead of flattening and losing all the spatial information of the input data, we use convolutional filters, which are arrays of numbers which slide over an image. So pixels from an input space to an output space are locally correlated. So the spatial information isn't lost between layers. And also with a dense neural network, each input pixel will be linked to each output pixel, meaning the very top left pixel of the input image is still wired up to the very bottom right pixel of the output image. So obviously this has this causes a problem, because in reality, in a picture, the top left pixel has very little to do with the bottom right pixels. So these ideas shouldn't really be correlated because they have nothing to do with each other. So a convolutional filter and a convolutional neural network fixes this concept. So I'm just going to delete this line as well for clarity. So once again, there's no point in changing this. We want to specify the entry shape, which is going to be this 28 by 28 by 1 pixel image. So the first thing we want to do this time is not flatten it, because we don't want to lose all that spatial information. We want to use a convolutional 2D filter, specifying that this is a 2D image, which obviously it is, because it's just an image, it's not a 3D model or anything. So as you can see, there are different overloads. This is a more complicated overload, which I'm not going to use, which you could specify a specific filter as a tensor to the model and specify the padding. But there is this overload, which is a much more user-friendly and easy to use overload, so I'm going to use this one. So first of all, I'm going to specify the size of the filter. So as I said, it's like a block, an array of pixels which will slide over the input space. So I'm setting the filter size to 5 by 5, and I could specify the depth of the filter, because not with this dataset, because it's grayscale, so it's only got one pixel in the depth dimension. Other inputs, and actually later on in this model, there will be more depth pixels. So if I could manually specify that I want this filter to have a depth of 1, but if I just leave that as blank, then it will automatically work it out with this helper function, so I don't need to actually specify that. So then I need to specify the number of filters, and again, I want this to run very quickly, so in reality I would use more than this, but I'm going to just say 8 filters. Okay, the padding type, this can either be valid padding or same padding. Basically, valid padding will reduce the output map space by this number -1 divided by 2, so 2 and 2 pixels. So if it was 28 by 28 when it went in, it would come out 26 by 26. But padding same will keep it the same size. So it's not, the details of that aren't very important, but I'm going to use padding same for this. Okay. And I can specialize a variable initializer, and because I didn't last time, I am going to, if I can spell it right, initializer. So this basically just lets me specify the mean and standard deviation of the sample that the random variable is sampled from. So by default, the mean's 0, which I'm not changing, and the standard deviation is 0.01. This is just float approximation to that number, but it is around 0.01, and I'm going to use 5 times 10 to the -2. Okay, like with the dense model, I'm then going to use a ReLU activation function, which just activates that to prevent linearities. Then I'm going to use a pooling layer, and what a pooling layer does is it just takes an input, and over each pool size, which I'm about to specify as 2 by 2, each pool of size 2 by 2, it will just take the maximum value and output it to the next layer. And the stride is just how far each pool steps along. So if I had a stride of 1 by 1, it would move 1 pixel at a time, and 2 by 2 will move 2 at a time. So I'm specifying 2 by 2 for this. And this will result in an image of half the size of that first layer. And I am going to add one more convolutional layer, which is going to be almost the same. Here is where I said the depth can be specified. So I could specify that as having a depth of 8, because this will output 8 filters worth of depth, whereas when this layer went into this layer, it only had 1 depth, so that should be 1 technically in there. But as I said, it will, if I just leave this as blank, it will automatically work out the depth that it should be. And again, I'm going to specify 8 filters just to make it run quickly, and same padding, and I'm going to use the same sample distribution. For the normal distribution, the random variables, the random initialization variables are sampled from, so that's fine. And again, calling the ReLU and then the max pooling with the same shape. So I'll keep a quick log of the different shapes at each layer actually. So when it comes into this layer, we have 28 by 28 by 1 pixels. So because this was the loaded size. Now, as I said, this padding same means that it's still going to be 28 by 28 pixels, but this 8 means that the depth is now going to be 8. So after this layer, it would be 28 by 28 by 8. However, I'm going to skip that because the max pooling, as I said, is going to divide these 2 dimensions by 2. So the input to this layer is going to turn out to be 14 by 14 by 8. And then this also has 8 filters out, padding same, so this is going to result in 14 by 14 by 8. And this is going to divide everything by 2 again. So when we get down to here, we're going to have 7 by 7 by 8 pixels for the image at this point. Now, this isn't very useful in terms of what I said before about specifying everything into 10 classes, because, 49 times 8, just under 500, about 400 variables is completely meaningless for 10 classes. So now what we want to do is transform this size into just 10 pixels. So what we're going to do is actually use a dense layer at the end of this. So to do that, first of all, you can't really multiply a 3-dimensional tensor of numbers with a matrix, so we need to flatten this, and this will just transform this into a string of 1-dimensional numbers with no shape. So this will then be of shape 49 times 8, so that's 392, I think. And then what we can do with this is just call a standard dense layer. And normally you would probably use an intermediary dense layer, but to make it, well, actually no, it's not going to make a huge difference to the training speed, so I will add this layer. So I'm going to use 384 nodes on this intermediary layer, and then finally, just like with the last dense network model, I'm just going to transform it into the number of classes as the output. Now, that should be all the changes that need to be made to make this a convolutional model. I think that should be everything, so I don't think I've made any mistakes or anything, I hope. So hopefully if I run this, and it's likely to run a little slower than it did last time, but hopefully it won't take too long, because I'd specified low numbers for the depth of the filters and stuff. So okay, so yeah, it's a bit slower, about 400 milliseconds, so what, about 10 times slower than last time we said. And again, you can see that the graph is clearly dropping off very quickly, just like it did with the dense model. And this should in general give a better approximation for the distribution, just because the type of model better represents the actual data, because it reserves the spatial aspects of the data. So hopefully it'll give a better model. It may not, just because I've simplified the parameterization of the model to make it run quickly. Although we did get this burst of taking a lot longer here, probably just because I've got other processes running at the same time. But yeah, this should give a good model, and we will see a percentage accuracy after it's evaluated in a few seconds. 91.5, so yes, as I said, it did actually get slightly lower accuracy. However, in general, a convolutional model will actually perform better if I gave it more epochs and more filters, and just gave it a slightly more powerful model. But as I said, it would take a lot longer to train. So I think that's about everything for this this part of the training process. So to just summarize again, loading the dataset, defining the model, training it, and evaluating it. So that has actually created a network model. However, at this point, it's not much use, because even though that only took, about 60 seconds, I think it said, it's not much use if I have to do that every single time I want to classify something. So there is an exporting to file function. So if I write model.export to file, and I won't actually do this, but I can now specify a folder in which the model will be saved and the name of the model. So I can write this to a file. It will be a binary file, so it won't make much sense to anything other than this program. But then I can load it back in with the static method in network model, import from file, specifying the same two parameters. So basically just exporting and importing a model to and from a file. So yeah, that's important, obviously, if you need to actually use the model for anything. Otherwise, it's a bit useless just to have to train it each time. So the other way of writing to a file is actually using checkpointing. So again, I'm not going to actually write this out fully, but I could set a checkpoint type for this this model. So when it's training, I can set checkpoint end none per epoch and per steps, and these are actually like a flag system. So if I wanted at the end and also at the end of each epoch, I could use a bitwise OR operator to specify both of these like checkpoint times. So so yeah, then I could specify. It's going to show me the corrections, the outer corrections. Yeah, so I can specify again, like I said before, the model folder and the model name, and then if I'd chosen checkpoint steps here, and then two empty strings for just the sake of demonstration, and then I can specify the number of steps it's going to checkpoint after. So for example, if I said 200, every 200 training steps it's going to output another checkpoint to a file. So yeah, checkpointing is obviously useful. For example, if the program's going to crash, maybe, If checkpoints are saved, then not all is lost if it's been training for many hours, for example. So checkpointing is obviously very useful for that. And then it just allows you to, as I said up here, I think, if you specify this as false, which it is by default, and you if you import from a file with the static method, then you will be able to just continue training from where you left off. So I think that's about all of the basics with using the API. Obviously, there's more datasets you can load than the MNIST, so there's the inbuilt loaders I've got are the CIFAR. Oh, I need to include the file, the header. I've got the CIFAR data loader. I think that's the name of the header. IntelliSense will tell me in a second, I assume. Yes, there we go. So this has a general CIFAR dataset loader, which will be able to load any dataset in the format of CIFAR. So you can specify the number of classes, you can specify the size of the images, and etc. So there are also some type-deft like preset ones. So there's the CIFAR 10 data loader, which is the standard CIFAR 10 dataset, which is just 32 by 32 by 3 color RGB images with 10 output classes. There's the CIFAR 100, which has 2 sets of labels. One has a fine set of labels, so there's 100 classes, and one has a coarse set of labels, which have 20 like superclasses, which contain 5 subclasses each, and so on. And then I created this one, the small dataset loader, which is just a slightly smaller. Slightly smaller image size, and this is because, in general, when augmenting this dataset, so making it bigger without actually adding any new information, you would crop the images randomly for the CIFAR 10 dataset to 24 by 24. So I just added that as a little helper class just to make it a little bit easier for that. But obviously, you could then specify any you wanted. So this is kind of fixed. So there's 3 different formats actually. There's the standard CIFAR 10, which just has 1 byte of label data. There's the coarse, which has coarse and fine, which have 2 bytes, and then I can't remember which way around, but actually it says up there, the first byte's the coarse label and the second's the fine label. So in general, you use CIFAR 10, which just has 1 byte of label, specify the number of output classes, say, I don't know, 25, and then the image size, I don't know, 64 by 64 by 3. And then you could create your own loader, which will load in this file format. So that's the CIFAR loader. Again, it works the same way. It's a batch iterator extender, so it can be used with training and evaluating and so on. And the other inbuilt loader I created was just a hierarchical image loader, I think the header's called. There we go. Which is slightly more general. Again, when IntelliSense loads up, it'll be useful. But what this will do is it simply you specify a folder which contains a number of subfolders, and each of those subfolders should contain a set of images, and basically it will take each of the subfolders as a different class. So if there's 10 subfolders with 10 images, you have a data of 100 images, and the labels are the folders, and the data is the images within the folders. So it just simply goes through a directory and finds all the folders and creates a dataset and shuffles it, etc. And it also scales all the images so they fit into the right size that's specified and such. So yeah, this is a slightly more general loader that you could use on a custom dataset, for example, if you downloaded some pictures off the internet and just put them in different folders of what they are. And once again, as I said with the other data loaders, it inherits from the batch iterator class, so it can be used within all the model functions like training and evaluating. So that summarizes most of the high-level API library. As you can see, it's quite diverse. You could solve quite a lot of problems with this as it is at the moment. So yeah, you could train it against a number of different data sets, including custom-made data sets, and it learns not incredibly quickly, but definitely quickly enough to actually be feasibly useful. So yeah, I think that summarizes everything. So that concludes this video.